Hello and welcome everyone to our weekly session titled Latest in Bitcoin Tech, where we go through the weekly Bitcoin Optech newsletter. And this week we'll be going through newsletter number 302, published on 15th of May 2024. As always, I'll go through the preface of letter so that we get an overview of the topic that the newsletter contains this week. This week's newsletter announces the beta release of a full node supporting UTreeXO and summarizes two proposed extensions to BIP 119 Optech template verify. Also included are our regular sections announcing new releases and release candidates and describing notable changes to popular Bitcoin infrastructure software. We have two news articles this week, and we'll probably spend most of our time with them, if not all. The first one being UTreeXO D. Okay, so if you all have been active on X or Twitter this week, then I'm sure you all must have heard about UTreeXO. Somehow or the other, UTreeXO D. This must have popped up on your timeline. Somebody must have retweeted or talked about it. As Saurabh just said, what's happened, what's happening in Bitcoin this week. So like yeah, a lot of people that I know have been discussing UTreeXO D. Let's go through it and try and understand what it is and what it aims to achieve. This project has been in the pipeline for quite some time, a few years. Okay, and now we have a full node, a beta version of it that supports UTreeXO. I'll just read through the news article to begin with. Release of UTreeXO Beta D. Calvin Kim posted to the Bitcoin Dev mailing list to announce the beta release of UTreeXO D, full node with support for UTreeXO. UTreeXO allows a node to store a small commitment to the state of the UTXO set rather than the entire set itself. For example, a minimal commitment can be 32 bytes and the current full set is about 12 GB, making the commitment on the order of about a billion times smaller. To reduce bandwidth, UTreeXO may store additional commitments, increasing its use of disk space, but still keeping its chain state roughly on the order of a million times smaller than a traditional full node. A UTreeXO node that also prunes old blocks can run in a small constant amount of disk space, whereas even pruned regular full nodes can have their chain state grow beyond the bounds of a device's storage capacity. The release notes posted by Kim indicate that the node is compatible with BDK-based wallets, plus many other wallets through support for Electrum Personal Server. The node supports transaction relay with extensions to the P2P network protocol for allowing the relay of UTreeXO proofs. Both regular and bridge UTreeXO nodes are supported. Regular UTreeXO nodes use the UTreeXO commitment to save disk space. Bridge nodes store the complete UTXO state plus some additional data and can attach UTXO proofs to blocks and transactions created by nodes and wallets that don't support UTXO yet. UTXO does not require consensus changes and UTXO nodes do not interfere with non-UTXO nodes. Although regular UTXO nodes can only peer with other regular and bridge UTXO nodes. Kim includes several warnings in his announcement. The code and protocol is not peer-reviewed. There will be breaking changes. UTreeXO D is based on BTCD, which may have consensus incompatibilities. So there's been a lot of talk in the Bitcoin tech community recently about how the UTXO set is increasing and it's becoming more and more difficult for people to use embedded devices to run Bitcoin nodes. Rather, you need a specialized hardware now to run a Bitcoin node, and devices that have a 4 GB RAM are more or less ruled out, and Raspberry Pis are more or less ruled out, and how people are experiencing 2 weeks, 3 weeks, even a month of delay in the IBD initial block download because the UTXO set has a lot of unspendable dust transactions. Okay, so UTXO D claims to be a diagnosis for that. Okay, to understand what UTXO D does, what UTXO basically does, let's first understand what UTXO is, which is a very elementary level thing, but let's refresh our memories. Okay, so would anybody like to take a shot at what UTXO is?
UTXO is unspent transaction output. You are talking.
Yeah, that's what I'm talking about. If you'd like to add anything,
I'm not completely clear about UTXO, but UTXO is simply unspent transaction output. So list of all the transaction outputs that are not spent. Basically, uh, it's a simpler way to say that these are the Bitcoin potential addresses that can be spent in future.
right, yeah. So UTXO is unspent transaction output. These are basically the outputs that are eligible to be spent. Okay. So every time a node sees a new transaction, it will verify whether the transaction is eligible to be spent or no, whether it's valid or no, whether it's consensus compliant or no. And one of the things that the node will check it for is double spending to ensure that the transactions output are in the UTXO set and they are eligible to be spent. So that's what a UTXO is, and all these UTXOs are stored at a place called the UTXO set, which in your Bitcoin repository is the chain state. So if any of you is running a Bitcoin node, okay, a full archival Bitcoin node that you have built and compiled from source. If you go into your Bitcoin folder on your computer and go into this folder called chain state, it'll approximately be 12 GB if you check its size. So that chain state folder is where your UTXO sits, okay? And the UTXO set has grown approximately 5x in the past 12 to 14 months. So it's gone from around 2.5 GB to almost 12 GB. It's grown exponentially. Uh, so what's UTreeXO? So now we know what is UTXO. So we know what is UTXO set. We know what's the purpose of UTXO set. Okay, so what's UTreeXO? Uh, UTreeXO basically what it does is that it compacts the UTXO set. Okay, so it takes all the UTXOs and it hashes them, and it treats each UTXO as a leaf in a Merkle tree. Okay, and then it keeps on hashing till we reach the Merkle root. So Merkle root, as you know, is a solution to a lot of problems in Bitcoin, and Merkle root has optimized a lot of things in Bitcoin. And here too, these people have used the Merkle tree to save data that is utilized on the hard disk to store the UTXO set. Okay, so how does this work now? UTreeXO is a proposal alternative to the UTXO set for allowing full nodes to obtain and verify information about the UTXOs being spent in a transaction. Okay, so you don't have to maintain the entire UTXO set. Okay, that's what UTreeXO aims to achieve, that without maintaining the entire UTXO set of 12 GB, you should still be able to validate a transaction and act as a full node. It is a hash-based accumulator that would consolidate the UTXO set in a Merkle tree, allowing users to maintain only the desired UTXO set and verify all other data. So instead of storing each transaction individually or each UTXO individually in your chain state, okay, what UTXO attempts to do is that it hashes each transaction, okay, and then it creates a Merkle root of it, and you just have to store the Merkle root of the entire UTXO set. And whenever a transaction comes, that transaction just needs to give you the Merkle proof. It just needs to prove to you that it is a part of that same Merkle root, and that is how you validate that a transaction is a valid transaction without having to store the entire UTXO set. Okay. Now there's more to it. Okay. For UTXO to be implemented, you need two types of nodes. Okay. First are referred to as compact nodes, and the second are referred to as bridge nodes. Okay. And the third are regular nodes. Okay. Because not if you cannot force everybody to comply with this mechanism. Okay, what if somebody does not want to store a UTXO root? Okay, somebody wants to store the entire UTXO set and doesn't want to comply with this proposal. Okay, you cannot rule them out of the network. So there will we be assume a situation where there are three nodes. Okay, first are regular full nodes. Okay, the ones that we are using today. The second are going to be bridge nodes, which is a new terminology or a new mechanism of node that we will introduce. And the third will be compact nodes. Okay, so imagine a P2P network in a post UTreeXO world that contains three types of nodes: the full node, okay, which you and I are running today in the pre-UTXO era, and two more nodes, compact nodes and block nodes. Now, what do these compact nodes and what do these block nodes do? We'll see it. We'll analyze what do these two nodes do. The compact nodes begin their role when a new transaction is created and it is transmitted through the network. At that point, the node takes the transaction, performs a cryptographic proof of the fact, and regenerates the UTXO tree of the chain to obtain the final hash. The proof of inclusion is then sent along with the transaction to other compact nodes till a consensus in the state of UTreeXO is reached. Okay, so what do compact nodes do? Okay, whenever a compact node sees a new transaction, okay, at that point, the node takes the transactions, performs a cryptographic proof of the fact, and regenerates the UTXO set. Okay, so the compact node already has the UTXO Merkle root. Okay, it already has the UTXO Merkle root. Okay, now it sees a new transaction. What is it gonna do? It's gonna hash that transaction. Okay, add that transaction to the Merkle root and to the Merkle tree and update the Merkle root. Okay, so I have a Merkle root with me. I see a new transaction. Okay, now I need to add that transaction or the UTXO in that transaction to my UTXO tree, right? And after I add a new leaf to a UTXO tree, it's obvious that the Merkle root will change. So the compact node, the moment it sees a new transaction, it takes that transaction, okay, and it hashes that transaction, okay, and it puts it in the Merkle tree that it already has, and it updates the Merkle root of the UTXO set. That is what a compact node does, okay. And in addition, okay, I'll read the last. I don't think I read this paragraph entirely. So yeah, at that point, the node takes the transaction, performs a cryptographic proof of the fact, and regenerates the UTXO tree of the chain to obtain the final hash. The proof of inclusion is then sent along with the transaction to other compact nodes till a consensus in the state of UTreeXO is reached. Okay, so then what will this compact node do? It will not only transmit the transaction. Currently, what happens in the P2P network is when a node sees a transaction, the node validates the transaction and sends the transaction further to other peers in the network. Compact nodes will see the transaction, okay, will validate the will create a cryptographic proof of inclusion, and then update their Merkle root, and then forward not only the transaction but also the cryptographic proof of inclusion that this transaction has been included in the UTXO set. And all the other compact block peers, when they see the transaction, they will take the transaction, validate it as they validate any other transaction according to the consensus rules, and then they will also validate the proof of inclusion, and they will also update their Merkle root. Okay, this is the task of a compact node. Now, apart from compact node, we also have bridge nodes. What do bridge nodes do? In addition to compact nodes of UTreeXO, there are also the bridge nodes of UTreeXO. The function of these nodes is to receive the standard transactions of the network and to carry out all the necessary process to be included in the tree. To achieve this, the bridge nodes contain the entire history of the blockchain and the complete UTXO list. Okay. So just now we discussed that what will a compact node do? It'll, whenever it sees a new transaction, it'll take that transaction, okay, it'll hash the UTXO, it'll put it in the Merkle tree, and it'll update its Merkle root, and it'll further send the transaction or gossip the transaction with its peers, and also the cryptographic proof of inclusion, okay. But just now we discussed that in Bitcoin you cannot force proposals down people's throats, right? So what if somebody does not want to run a compact node? What if somebody does not want to comply with this UTreeXO proposal? They want to keep on running the node that they were running in the pre-UTreeXO world. Okay. Now your compact node is sharing a transaction, and along with the transaction, it is sharing a cryptographic proof of inclusion. Okay. But the node that is not compatible with UTreeXO does not understand that cryptographic proof that is coming its way, okay, nor can it share that cryptographic proof, okay, with compact nodes. So in that situation we need a bridge node. What's a bridge node? A bridge node, as the name suggests, is a bridge between a compact node and a full node. Okay, what will a bridge node do? In addition to compact nodes of the UTreeXO, there are also the bridge nodes of UTreeXO. The function of these nodes is to receive the standard transactions of the network and to carry out all the necessary process to be included in the tree. To achieve this, the bridge nodes contain the entire history of the blockchain and the complete UTXO list. Okay, so the bridge nodes will take the transactions from the full node, okay, and create a cryptographic proof of inclusion and share that proof with the compact nodes, okay. And when the compact nodes sends the transaction and the proof of inclusion to the bridge node will only further forward the transaction without forwarding the proof of inclusion to the full node. So bridge nodes basically ensure compatibility between compact nodes and full nodes. Okay, there is no way in which the compact node can directly communicate with the full node, and there is no way in which the full node can directly communicate with the compact node. Okay, because the full node is only interested in sending and receiving transactions, and the compact node is sending proof of inclusion along with the transaction. Okay, so you need a bridge node. Okay, what the bridge node will do is it'll take the transaction from the full node, it'll add a proof of inclusion, and it'll send the transaction along with the proof of inclusion to the compact node, and it'll take the proof of inclusion and the transaction from the compact node, and it'll only forward the transaction to the full node to ensure that there is no soft fork and there is compatibility between compact nodes and full nodes. So as you can see, where this is on LHS on the left hand side, if you can see, we have a communication between two compact nodes. Okay, so when two compact nodes are communicating with each other, they are sharing both the transactions and the proof of inclusion as well. Okay, so this node can share transactions with this node, and this node can share transactions with this node, and this node can share proof of inclusion with this node, and this node can share proof of inclusion with this node. Okay, and here we have two full nodes communicating with each other. Okay, these are the full nodes as we know them in a pre-UTreeXO world. Okay, they are not sharing any proof of inclusion with each other, they are just sharing transactions to and fro. Okay, and here we see the full nodes are communicating with bridge nodes. Okay, they are only sharing transactions, but the bridge node is adding proof of inclusion and sending it to the compact node. Okay, and this node is also only sharing the transaction, but the bridge node is adding the proof of inclusion and sending it to the compact node. And the compact node is sending the proof of inclusion and the transaction. The bridge node is only sharing the transaction further with the full node. So, like in a post UTXO world, these are the three types of nodes, or these are the three types of behaviors of nodes that will exist. Okay, now what's the basic difference between these three types of nodes? Okay, a full node, as we know, can be a pruned node and can be an archival node, right? A full node can either store the entire blockchain history from the genesis block, or it can store some part of the blockchain, or it cannot store the blockchain at all. It just needs to have the chain state, it just needs to have the latest UTXO set for it to be referred to as a full node. A compact node will not have the chain state at all. It will not have the UTXO set. It will have only UTXOs that belong to it. Okay, so it will only have UTXO set that belong to it. Other than that, it will only have the accumulator root. It will only have a 12 KB Merkle root using which it will validate transactions. A bridge node will have an accumulator node. It will have the entire Merkle tree, and it will also have the entire blockchain to validate the transactions. Okay, so when there is an incoming transaction to be, uh, can everyone mute themselves, please? Somebody's not muted. I think Bala, can you please mute yourself? Unless your 3-year-old Bitcoiner has some questions. When there is an incoming transaction to be validated, the spender can provide a Merkle proof to show that their coins are contained in the Merkle root. The UTXO is verified and then deleted. A new UTXO is created for the recipient of the transaction, which is added as a new leaf and the Merkle to the Merkle tree. The leaf is then hashed, combined with all other UTXOs, and the Merkle root is updated. So there are basically two responsibilities of a compact node. Okay, whenever a new transaction is coming, you destroy UTXO and then you create a new UTXO, right? You cannot create a UTXO without destroying an earlier UTXO. Okay, so what the compact node has to do is that it has to delete the existing UTXO from the Merkle tree, and it has to append the new UTXO that this transaction is creating to the Merkle tree, and then it needs to update or upgrade the Merkle root, and then it needs to store that Merkle root, and then it needs to pass that transaction along with the proof of inclusion. Okay, so I'm just giving an example or an illustration of how this would look. So assume that there is a compact node that has 8 transactions. Assume there are only 8 transactions that have happened, or we are considering a subset of the transaction history of Bitcoin, which has 8 transactions: transaction 1, transaction 2, transaction 3, transaction 4, 5, 6, 7, and 8. Okay, so these transactions, or the cryptographic hash of these transactions, will be treated as leaves. Okay, and these will be the nodes. So you hash two leaves to get a node, you hash these two leaves to get a node, you hash these two leaves to get a node, and you hash these two leaves to get a node. Then you hash two nodes to get another node. Then you hash these two nodes to get another node, and then you hash these two nodes to get that which is referred to as the accumulator root or the Moku root. Accumulator because it accumulates all the information. So it's known as the accumulator root or the Moku root. So the compact block will only store this. It will only store the accumulator root, and every time it sees a new transaction, it will just need the transaction. I mean, it will just add the transaction to delete a UTXO and add the new UTXO to the UTXO set and update the accumulator root. That is what it will do. UTreeXO nodes will only store the accumulator root. So UTreeXO nodes only need to store 12 KB of data and not 12 GB of data. Now let's say that TX7 is deleted. Okay, so let's say we see a transaction such that this UTXO which already exists in the UTXO tree is deleted. It's being destroyed. From the Merkle tree, we would end up with a forest of Merkle tree and 3 Merkle roots which be stored by the accumulator. Okay, so like it's not always necessary that your UTXO tree will be symmetrical or that which is known as forest. So basically, except for your root, everything else is known as the forest. This is the Merkle forest. So it's not always necessary that your Merkle forest will be symmetrical. Okay, it might even be like this. In this situation, this will be your Merkle root. Okay, so you hash these two transactions, you get a node. You hash these two transactions, you get a node. When you hash these two nodes, you get another node. Okay, when you hash these two transactions, you get a node, and you don't have a pair for the 8 transactions. So the 8 transactions cryptographic hash itself goes in the Merkle root. So this is your Merkle root or your accumulator node, which the compact node needs to share. Okay, so this is the proposal of UTreeXO. What it tries to do is that instead of storing the entire UTXO set, which is approximately 12 GB, you can store only uh, 12 KB. I believe it's 12 KB or 32 KB. Let me just check. 32 bytes. Sorry. I was talking KB. Sorry, 32 bytes. Instead of storing 12 GB, you can now only store a 32 byte. Right, because that's the output of a SHA-256 cryptographic hash algorithm. So only 32 bytes. Instead of storing a chain state, like I just said, if any of you are running a Bitcoin node and you have built and compiled it from source, after the session, you can go into your Bitcoin folder and search for this folder called chain state where your UTXO set is. Okay, and you can right click and see the size of that folder. It'll be around 12 GB and it can be reduced to 32 bytes with UTXO by just storing the accumulator root, and you can validate the transactions by just using the proof of inclusion and to make and assuring that the transaction or the UTXO is in the UTXO set. You don't have to store the entire chain state. Okay, that is what it does. And this post also has some interesting information. UTXO D is basically the name of the node. Okay, UTXO is the name of the proposal. UTXO D is the node that supports UTXO. Okay, and its beta testing is being done by Kim Calvin or Calvin Kim. I think he's an HRF grantee. Some relevant information that we can read through. Okay, it's not very long. Hi all. UTreeXO D, a full node implementation with UTreeXO accumulator support, is now available for general testing by the public. Notable features are implementation of efficient UTreeXO accumulators with an improved deletion algorithm from the UTreeXO paper, efficient P2P transaction relay with support for caching UTreeXO proofs for mempool transactions, quick sync to the tip of the blockchain with Assume UTreeXO. Has anybody heard about Assume UTreeXO? What it is? At least heard about it, even if nobody, if anybody is not aware of what exactly it is. Has anybody heard this term, Assume UTreeXO?
Have we
It's a
covered it
system.
in any previous session? I think I
No.
might have heard it in Bitshala. Okay, no, then I don't think I've heard it.
Uh, One community member wanted to review this PR, so they posted that their tests are failing. Maybe there you might have heard this word Assume UTreeXO at
Hmm.
Bitshala, but we've not covered it in any of our sessions. Okay, so what's Assume UTXO? What happens is that if you are running a node, okay, what happens is referred to as IBD, initial block download. Okay, first your node downloads all the transactions and all the blocks and validates all the transactions and all the blocks and first it validates all the headers. Okay, and then it validates all the transactions on all the blocks. Okay, and that takes a lot of time. So like Like some people, if they have a plan of running a node on Raspberry Pi, then be prepared for it. Your IBD is going to take approximately 2 weeks. So you will understand exactly what an upgrade Assume UTreeXO can be. Okay, and your wallet cannot function until and unless your IBD is not done. Okay, because if you're running any implementation of Bitcoin, okay, and you intend to use its own wallet, for instance, if you're running Bitcoin Core and you intend to use Bitcoin Core's wallet, then your IBD needs to be complete, right? Your wallet needs to have the entire UTXO set. Your wallet needs to have validated all the transactions and all the blocks and have all the updated information. Only after that, your wallet can start sending and receiving payments. Until and unless the entire blockchain from Genesis block to the final block has not been validated by your full archival node, and the UTXO set is not updated till the chain tip, cannot accept and receive informations, right? Information. So what Assume UTreeXO does is that it it validate. I mean, I my high level assumption is that it does validate the Merkle tree. Basically, it validates the Merkle tree. Or I think no, it does not validate the Merkle tree. I think it validates the headers. Sorry, yeah, it will validate the headers. It will validate the headers, and it will start functioning as a wallet. So you not have to wait for the entire blockchain to sync. Your node will validate the headers, and I believe it will also validate the transactions using the Merkle tree. It also creates a Merkle tree and it validates all the transactions using that Merkle tree. So you have all the information that you need to send and receive payments before the entire blockchain is in sync. So you don't have to wait for 2 weeks if you're running a node on Raspberry Pi, or if you're running a node on whatever. It will take generally 2 days at least. You don't have to wait for that tenure. Okay, so your node will validate the headers, and then I believe using a Merkle tree, it will validate all the UTXOs. And once you have the UTXOs validated and you have the block header hashes, then you're good to go. You can start sending and receiving payments. You don't have to wait for the entire blockchain to sync. That is what Assume UTreeXO does. So yeah, this UTreeXO D node supports Assume UTreeXO built-in wallet support for BDK wallet. So if you're running a node with UTreeXO, it will be compatible with wallets that are built on BDK and Electrum personal server, Electrum wallets as well. It'll also support Electrum servers. So if anybody's planning to run this node, then they can use Electrum wallets and BDK wallets that are built on top of BDK to send and receive transactions, even though it's in the beta phase. It's important to note that the code and protocol is not peer reviewed. Using the node for production usage or for non-negligible amounts of Bitcoin is not recommended. There will also be breaking changes requiring frequent updates as well. Bitcoin node implementation it's basically built on BTCD, right? As we know that there are different implementations of Bitcoin. There's just not one implementation. BTCD is another implementation of Bitcoin, which is in Go. Okay, so UTXO has been incorporated into this implementation. You can't use it right now with Bitcoin Core or any other implementation. You will only be able to use it with BTCD, and the only wallets that are compatible with it are Electrum wallets and BDK wallets. So yeah, that is what is a UTreeXO D node, and that is what is UTreeXC. And we talked about compact nodes and bridge nodes and how they communicate with each other, and how UTreeXO plans to make the initial block download quicker, and how it wants to reduce the burden of storing the entire chain state from embedded devices. So yeah, that is all I had to cover. Any questions, any suggestions, any thoughts, please feel free to go ahead and talk.
Is there any criticism of UTXO because it feels like a really good innovation? Is there any good reason to not? Hmm.
I cannot validate this information. I have heard a few people say that it increases your reliance on bridge nodes. You have to
Hmm.
trust the bridge nodes, okay? Because currently what happens is that all nodes that are active in the P2P network can communicate with each other, okay?
Hmm.
But here what happens is that the compact node cannot communicate with the full node, right? Because the language that the compact node speaks, it sends transactions and proofs. And the
Right.
full node does not understand the proof, and the full node will send transaction without the proof. The compact node needs the proof. So you always need a bridge node to
Hmm.
route information from a full node to compact node, And thus, I have heard a few people talk about it on social media that it increases your reliance on bridge node. I cannot technically verify how sound that criticism is, but yes, that is one criticism that I have heard of.
Right. No, makes sense. Makes sense. I think bridge node requires somebody to also run a full node and also be able to communicate with UTXO nodes. So yeah, I don't think there's a risk that there's not enough bridge nodes, so you're relying on some bridge nodes. So that's a good concern. But I think eventually we will see UTXO getting adopted. Is there any technical reason you see that there's some trade-off with not keeping the entire chain state on your node?
Uh, I mean, firstly, like you said, but I mean, the thing is, there need to be adequate number of bridge nodes, right? Even if there are, even if we say there's no compromise in trust, okay, but bridge nodes need to be adequate in number. If there are very few bridge nodes, then the communication becomes very slow and there's latency. So there need to be adequate number of bridge nodes, okay. And as far as this being adopted is concerned, then I mean, a lot of testing will have to do, right?
Right.
Because if you incorporate anything in Bitcoin, you will also have to see currently, these people are testing it on BTCD. It needs to work with Bitcoin Core. It needs to work with all the other implementations. It needs to be compatible with Lightning Network as well, right?
Mm.
Because you're going to make commitment transactions, you're going to make funding transactions. So you've got to test it with the Lightning Network. You've got to test it with multiple implementations of Lightning Network. You've got to test it with multiple wallets. You've got to test it with multiple implementations of Bitcoin Core, and then probably it'll get implemented. So it's something that is being worked on since quite some time. We're talking about this right now because a beta node has been developed, but UTreeXO is something that people have been working on since quite some time. I'm sure you've heard the name Taj Reja, the
Mm. Yes.
co-author of Lightning Paper. I think he came up with this concept, and he's been working on it since quite some time. And now Calvin Kim is working on it with a group of other developers. So Utrix, so this proposal has been there for quite some time. The proposal is not new. It's been there for a few years, I believe. We're talking about it today because a beta node has come out, and the testing of the beta node is being done. So that's why I'm talking about
Mm.
it. So I still feel it's a long journey. It's still in its
Right.
infancy stages. It'll take time, maybe even years.
Makes sense. Makes sense. And I think that's UTXO set is the majority of memory that Bitcoin full node runs, or is there some other element to it? If we are
No,
able to. Hmm.
I mean, it depends on what node you're running. If you're running a full archival node, then the majority of the disk space will be utilized by the blockchain. UTXO is just the UTXO. Blockchain is the entire transaction, the input, the output, the everything, the entire block. And that currently, as it stands, is I believe around 700 GBs.
Hmm. Hmm.
Okay, so that is the major chunk of information. After that, it's the UTXO set. But the thing is that you don't have to necessarily store the entire blockchain, right? You can run a prune node and prune the blockchain. You can even discard the entire blockchain. You don't even have to store the entire blockchain. You can still be a full node without having the blockchain at all. Okay, but the chain state you cannot discard. Okay, even if you're a prune node, you need to have the chain state. You need to have the UTXO set. Okay, even if you are a full archival node, you need to have the chain state. So that is something you can't do away with. As far as the blockchain is concerned, then the prune nodes can do away with it, and even the full nodes can do away with it. It's only the archival nodes that store it. But as far as the chain state is concerned, then the prune nodes needed, and the archival nodes also needed. You can't do without it. You can't be a full node without the chain state.
Right. Right. Makes sense. Thanks.
All right. So with this, you can run a full node on with just the 32 bytes of memory. I mean, you obviously need more than that, but I'm just saying because you can remove the entire blockchain, you can remove the entire chain state, and you can just have an accumulated root. So 32 bytes is all you rely on to run a full node.
And where else is Merkle root used in Bitcoin? It's used in.
Transaction data.
Yeah. Yeah. Thanks. Yep. Yep.
Uh, One more thing, Fazil. So we were talking about storage, and prune nodes are a solution for your storage problems. I think what UTXO sort of helps us is sort of reducing the RAM usage as well. So though most of the blockchain data gets stored in SSD, it's the UTXO is what gets is what gets consumed by RAM, right? Am I right in saying so? Like because you need regular access of this memory, of which UTXO has been spent and which UTXO has not been spent, or that's like some random, like, is that true or is that not true?
I think your RAM comes into play in optimizing your IBD. Okay, so if your device, the device that you are using, does not have a good hardware specification and is not able to validate the transactions quickly, in that case, your RAM memory is used to store the data set. So that is where it comes into play. It is a question that has been triggering me as well. In fact, I even reached out to a couple of people that I look up to because I wanted to get into the detail of it. Because even I keep hearing that your RAM gets bloated because of the bloating of blockchain. And even I was of the assumption that the blockchain and the chain state, everything eventually gets stored on the hard disk, not on your RAM. But yeah, I was informed recently that your RAM does come into play if your initial block download is taking a lot of time, then your chain state gets stored partially on the RAM, or something on those lines. But I mean, recently I've reached out to a couple of people to share some resources with me so that I can understand in detail how exactly a bloated UTXO set impacts RAM. So yeah, when I am fully aware of it, I'll share the technical details of it with you. But yes, it does have an impact on RAM. I've heard a lot of people talk about that, a lot of Bitcoin developers as well. How exactly does that have an impact on RAM? I have an overview understanding, but not the technical intricacies. But I'm really keen on learning. That's a very important thing to learn and understand. So if I have any resources, hopefully in the near future, I'll share with you as well. But yes, it does have an impact. How? The technical details, I'm not really well versed with the technical details.
Okay, thanks, Fatih.
Yeah, welcome. Okay, yeah. Where else is Mockle? Where else are Mockle trees used? Like Saurav mentioned. I mean, firstly, in the block, right? We have a block header hash. Was that? I mean, we have the Mockle root, right? How are transactions arranged in the block? They're not arranged linearly. They are arranged in the form of a Mockle tree. So whenever you get a transaction, okay, you hash that transaction. You take the input, the output, and all the other metadata, and you hash that transaction. Okay, and that hash of a transaction is a leaf, and then you keep on hashing till it accumulates a Mockle root, and that Mockle root is 32 bytes. You put it in the block header, and with SegWit blocks, we have like two Mockle roots. One Mockle root is of the transaction itself, the input, the output, and other metadata, and the other Mockle root is the witness. Okay, the witness, we also hash each witness, so we have two Mockle roots now. One of the transaction, which has the TXID, and other of the witness data, which is the WTXID. So we have two Mockle roots and two Mockle trees in every block. The LLSA Mockle roots use tap scripts. Okay, even in the tap script, like all different permutations of scripts are hashed and converted into leaves, and then you make nodes, and then you have the Mockle root of the tap script, and whatever script you want to spend, you just present that script and the proof of inclusion. You don't have to share all the scripts. So like tap scripts and header hashes, trap scripts and Mockle roots of transactions are two places where we already use Mockle trees, and I'm sure there are a lot of other places where we use Mockle trees. But yeah, this could be a third implementation at least. Yeah, so that is all I had to share about UTreeXO. Let's go to the second news article. BIP 119 extensions for smaller hashes and arbitrary data commitments. Jeremy Rubin posted to Bitcoin Dev mailing list a proposed BIP to extend the proposed Optech template verify OpCTV with two additional features. Support for hash 160 hashes. These are the hash digests used for P2PKH, P2SH, and P2WPKH addresses. They are 20 bytes compared to 32 bytes. 32-byte hash digests used in the base BIP 119 proposal. In a naive multi-party protocols, a collision attack against a 20-byte hash can be performed in about 2 to the power 80 brute force operations, which is within the reach of a highly motivated attacker. For this reason, modern Bitcoin opcodes typically use 32-byte hash digests. However, security in single-party protocols or well-designed multi-party protocols using 20-byte hashes can be increased to make compromise unlikely in less than about 2 to the power 160 brute force operations, allowing those protocols to save about 12 bytes per digest. One case where that might be useful is in implementations of the L2 protocol. Support for additional commitments. OpCTV only succeeds if it is executed within a transaction that contains inputs and outputs that hash to the same value as the provided hash digest. One of those outputs could be an operator output that commits to some data that the script creator wants to be published to the blockchain, such as data necessary to recover LN channel state from a backup. However, putting data in the witness field would be significantly less expensive. The proposed updated form of OpCTV allows the script creator to require that an additional piece of data from the witness stack be included when the inputs and outputs are hashed. That data will be checked against the hash digest provided by script creator. This ensures that data is published to the blockchain with minimal use of block weight. By now, most of us know what OpCTV is. It's a proposed opcode with the intention of achieving covenants. Okay. And the template here refers to the set of conditions based on which you want to spend the transaction. Okay, that is your template here. Okay. Now, when you are hashing that template, you were using a hash operation that gave you a 32-byte digest. Okay. Now, there is a proposal to make some changes to OpCTV and incorporating 20-byte hashes. Okay. So, an example of 32-byte hash digest is the output of a SHA-256 algorithm. And the example of a 20-byte digest is the output of a hash 160, that is a SHA-256 followed by write-MD 160. Okay. So instead of using a hash functions that hash your template to 32-byte digests, this update proposes to use hash functions that hash the templates to 20-byte digests. Okay, so whatever is your input or your output that you are binding the transaction to, whatever are the conditions based on which you want to spend the transaction, those conditions are being proposed to hash to a hash 160. Okay, and save 20 bytes and save 12 bytes, sorry. Okay, so I mean 20 bytes, the possible of a collision attack in 20 bytes is higher than the possible of a collision attack in 32 bytes, but the trade-off is that you save 12 bytes. The trade-off is that you save 12 bytes. So that is one proposal to reduce the size and optimize the data storage by using a hash function that gives a 20-byte output for the template that you want to hash. The second update that this proposal suggests for OpCTV is
The proposal
now
is this
sorry?
proposal of CTV is there for ordinals? Like, what is the end use case for this?
Covenants.
Covenants. Okay, sorry.
Yeah. So basically what the template is, like we've discussed covenants, right? How covenants lock the output of a transaction. Okay. So if Alice wants to pay 1 Bitcoin to Bob, Bob can create a template and say that I will send this 1 Bitcoin to Charlie. Okay. And lock that transaction to Charlie's address. Okay. So when Alice sends the transaction to Bob, Bob can only further send it to Charlie. Okay. That is what a covenant is. How this helps is that if somebody, for instance, hacks into Bob's wallet, they can do nothing. They cannot send that transaction to their own address, okay, or anybody else's address. Bob wanted that transaction to go to Charlie. That transaction will only and only go to Charlie, okay. So the conditions that you stipulate before spending a transaction, the transaction will only be spent based on that condition, and that condition is known as a template. You create a template and you log the transaction with that template and you hash that transaction. Okay, you hash that template. Okay, and when you're spending the transaction, the conditions based on which you are spending that transaction, if those conditions are hashed and they match with the hash that you submitted earlier, then you can spend the transaction. So we were using 32. I mean, the proposal suggested initially 32 bytes, and now it suggests 20 bytes. So you save 12 bytes of data. This is one proposal. I mean, the BIP is already there, but like what you can say, an upgrade or an addition to the already suggested proposal. Another one is that yeah.
Yeah, sorry, just one point that do you mind going over the last sentence of this paragraph? I'm not sure if I followed this from here. However, security in single party protocols or well-designed multi-party protocols using 20-byte hashes can be increased to make compromise unlikely in less than about 2 to the power 160 brute force operations. Does that make sense? I'm not able to follow it.
Okay, so basically when I mean, if you're using a mathematical hash function that takes in an arbitrary data arbitrary length and gives you a fixed output, right? That's what SHA-256 does. Okay, let's talk about SHA-256. Okay, you can give any input to SHA-256. My name is Shreyan. Okay, and it will give you an output of 32 bytes. Okay, you can give it an entire essay, an entire book. It will still give you a 32 byte output. Okay, now the 32 byte output can be collision resistant. I mean, they can be collisions, right? We say it's highly infeasible, but we never say it's impossible. It's possible. Right? It's possible that you can give two different pieces of information. You can give it my name is Shreyan and my name is Faisal, and it'll hash it, and the output will be same. Okay, there is a possibility. And
Right.
with 20 bytes, the possibility is higher. Okay, if your mathematical hash function gives an output of 32 bytes, and there's another mathematical hash function that gives you an output of 20 bytes, the possibility of collision in 20 bytes is higher than that in 32 bytes. So if an attacker is trying to brute force, the chances for him to break the hash function that gives a 32 byte digest is less, and that of 20 bytes is high. Okay, so when you're using a hash function that is 32 bytes, we were using 32 bytes, right? SHA-256 is what was proposed to hash the template, but now hash 160 is being proposed. So you save 12 bytes, but the chances of collision resistance goes up, right? So for this, so if I read the entire thing, they are 20 bytes compared to 32 byte hash digest used in the base BIP 119 proposal. In naive multi-party protocols, a collision attack against a 20 byte hash can be performed in about 2 to the power 80 brute force operations. Okay, so if you perform these many brute forces, brute force is just randomly guessing. Okay, if you randomly guess, so if you perform these many brute force operations, okay, there is a chance of you cracking a 20 byte output, right? So if I give you a 20 byte output, okay, and
Right.
you brute force these many times, you can guess what the pre-image was.
Right.
Okay? With a 32 byte output, that's higher. That's higher. Okay, so now you're compromising on your security. Okay, which is within the reach of a highly motivated attacker. So it is within the reach. Okay, it is with these many brute forces is within the reach of a highly motivated attacker. For this reason, modern Bitcoin opcos typically use 32 byte hash digests. Okay, even in the TypeScript we use 32 byte hash digests. However, security in single-party protocols or well-designed multi-party protocols using 20 byte hashes can be increased to make compromise unlikely in less than about 2 to the power 160 brute force operations. Okay, so there is some nitty-gritty, there is some mumbo jumbo, there is some cryptography that you can do to optimize a 20 byte hash output and make the attacker perform these many brute force operations instead of these many brute force operations. Okay, so even though we are compromising on the security, there are mechanisms, there are protocols in place that we can deploy to enhance the security of a 20 byte digest to these many brute force operations.
Makes
So
sense.
this
Right.
is like a counter for those people who might say that, hey, we're saving 12 bytes, okay, but we're increasing the possibility of collision resistance. So the counter to that is that the author proposes that we will come up with cryptographic measures to ensure that even though the hash digest is 20 bytes, it will not be compromised, or it cannot be compromised, or it's infeasible to compromise it in less than these many brute force operations.
Right. Makes sense. Yes. Thanks.
Okay. The second proposal is support for additional commitments. Okay. Let's read this again quickly. OpCTV only succeeds if it is executed within a transaction that contains inputs and outputs that hash to the same value as a provided hash digest. Okay, so what's the template? The template is not the entire transaction. Okay, we don't put the entire transaction of the script. We only put the conditions to which we have logged the transaction. Okay, if I'm saying out of this 1 Bitcoin, I will only spend 5 Bitcoin to somebody else's address, and the other 5 will come as change to my address. Okay, only that information to which the transaction is quote unquote locked, only that is the template. You don't have to use the entire transaction as a template. Only the conditions that you have stipulated, only those conditions are put as a template. It could be the input, it could be the output, it could be some other metadata. Okay, so OpCTV only succeeds if it is executed within a transaction that contains inputs and outputs that hash to the same value as provided hash digest. Okay, so when you're trying to spend the transaction, it'll see the inputs, it'll see the outputs, it'll hash the data, and it'll see if it matches with the template or the hash digest that you provided earlier, right? That is what we do even in the Lightning Network, right? You share a hash, okay, and when then the pre-image comes, and then you hash the pre-image, and then you see whether both the hashes match. That's also what we do in P2SH, okay? You share the redeem script, then you hash the redeem script, and you already have the hash of that script. You see if that matches. We do that in P2P cache as well, right? We send the public key, we hash the public key, then we compare the wallet address, which is nothing but the hash of the public key. We see if both the hashes match. That's what we do in OpsCTV, right? We hash the template, we put it on the script. When we're trying to spend the transaction, we reveal the conditions on which we are spending the transaction. Those conditions are then hashed and then are matched with the previous hash that we submitted. And if both the hashes match, then the transaction can be spent. Okay. Now, one of those outputs could be an operator, right? Because OpsCTV has inputs and outputs, right? This is what you commit to. You commit to the inputs and you commit to the outputs. Okay. The outputs of a transaction can also have operator, which can have some metadata. Okay, that commits to some data that the script creator wants to be published to the blockchain, such as data necessary to recover Allen channel state from a backup. Okay. However, putting a data in the witness field would be significantly less expensive. The proposed updated form of OpsCTV allows a script creator to require that an additional piece of data from the witness stack be included when the inputs and outputs are hashed. That data will be checked against the hash digest provided by the script creator. This ensures that the data is published to the blockchain with minimal use of block weight. Okay, so if you want to embed some arbitrary data, it can be done via operator, right? That is what Satoshi used, right? We all know in the Genesis block, he put the headline of that newspaper, right? The chancellor on the brink of another bank bailout or something on that line. He put it in the operator, okay? And I'm sure you all must have heard that a lot of arbitrary data, whether it's inscriptions, whether it's runes, okay, not runes, but inscriptions, BRC20 tokens, they are put in the witness field, okay? They don't put it in the operator, they put it in the witness script. Can anybody take a shot at, even though you have an operator where you can put embedded data, why is that data instead of operator being put in the witness script of transactions? Why are inscriptions not being put in operators and why are they being put in the witness data?
Because of the witness discount?
Exactly. Because you have to pay 3 times less.
4
As
times,
compared
right?
to the
Is it 3 times? I'm not
no,
sure
I mean,
myself. Okay.
if
I
yeah,
think it is times.
no, it's 4 times. I was using some other math, but yeah, it's 4 times. Yeah, it's 4 times. No, guys, 3 times. Sorry, 3 times. Three
Right,
times. It's
I'm not
three
sure
times.
myself. Okay. Yeah.
No, I'm sure 3 times.
Hmm.
Okay, that entire 4 thing is that your regular data gets a count of 1 and your witness data gets a count of 3. So 1 plus 3 is 4. So when we say the block can go up to 4 virtual MB, it means that the actual block will be 1 MB. Okay, 1 virtual MB, and the witness data will be 3 virtual MB. So that 3 plus 1, the entire thing is 4. So we keep
Right.
hearing that 4 MB, 4 MB, but the witness is 3 times, and the input and the output and other metadata is 1 time. So it's 3. Okay, so that is why it is being used. Okay, so what is being done is, up till now, using CTV, if you wanted to embed any arbitrary data, which in occasions might also have a use case. Okay, we're not ruling that out. There might be situations where there might be an actual use case. An operator is a mechanism through which you can embed data in a very less harmful manner, because there are a lot of ways using which you can embed arbitrary data into the blockchain. Operator is probably the least harmful. And that is why maybe Satoshi had operator, and maybe that is why Satoshi used it to embed arbitrary data to show that, hey, if there is a use case for arbitrary data, use this because this is the least harmful mechanism of doing it. Okay, so in an OpsCTV transaction, if you want to embed any arbitrary data, you can put it in operator, right? Because operator is a part of output, okay? And output can be included in a template, okay? But witness data cannot. So what if somebody wants to put arbitrary data in witness and avail discount? Okay, in that situation, what this proposal says is that there should be a mechanism for you to also put arbitrary data, okay, in the OpsCTV transaction other than operator as well. Okay, how is that possible? One of those outputs could be an operator output that commits to some data that the script creator wants to publish to the blockchain, such as data necessary to recover Allen challenge state from backup. However, putting data in the witness field would be significantly less expensive. The proposed update from form of OpsCTV allows the script creator to require that an additional piece of data from the witness stack be included when the inputs and outputs are hashed. Okay, so let's say the OpsCTV hash is 20 bytes, like we discussed. Okay, so one mechanism could be that they, okay, if you see that your template or your hash digest is 20 bytes, it means that it does not have any arbitrary data in the witness. Okay, but if it has an arbitrary data in the witness, then maybe you can add 1 byte flag to there over there. Okay, so instead of 20 bytes, you append a 1 byte flag. When the script reader sees that there is a 1 byte flag, okay, then it understands that there is some arbitrary data in the witness which also needs to be verified. Okay, so this is a proposal, a high level proposal of how you can do it. Okay, so if your hash digest is 20 bytes, you don't have any arbitrary data in the witness. If it's 21 bytes, then 20 bytes is the template, and 1 byte signals that you need to go into the witness data and pull out some arbitrary information. Okay, that needs to be verified. Now, where can this have a use case? This can have a use case as claimed in L2 protocol. We've covered L2 protocol in one of our preceding sessions. What's an L2 protocol? It's also known as error symmetry. We've talked a lot about how Lightning channel functions, even in the book Mastering the Lightning Network, and even in our latest in Bitcoin Tech sessions. And we've talked in detail about revoked commitment transactions, right? Where a cheater tries to broadcast a revoked commitment transaction. Okay. Now, if the honest counterparty's node figures out that a revoked commitment transaction is being broadcasted, the honest party's node can levy a penalty on the cheater and thereby take all the funds that are in the Lightning channel. Okay. But what L2 proposes is that the revoked transactions immediately become invalid. They cannot be broadcasted anymore. Okay. So the moment the state of the Lightning channel is updated, the previous commitment transaction gets invalid. So if you try to broadcast it, the first node across which it will come will reject it and it will not propagate it anymore. Okay. Now it is also possible that somebody might lose the state of their Lightning channel. Okay. So they can put some arbitrary data in the commitment transaction that helps them recover the state. Okay. So because whatever happens in the Lightning network, whenever the state is updated, no information is passed on to the main net. Okay, that commitment transaction is not broadcasted. So every time you create a new commitment transaction and you update the state of your Lightning channel, you can keep some information pertaining that state that helps you recover the state, just in case you lose the state in that in the witness data of that commitment transaction of the Lightning network. Okay, so when you are trying to furnish that commitment transaction, you can retain the state using that commitment transaction. This could be one use case that is proposed. So instead of putting it on the operator, you put it in the witness data. Okay, and then from the witness data, it can be fetched. Whether you agree with it or whether you don't agree with it is open to argument and discussion. But this is what the proposal says. It proposes that people who are using OpsCTV should be allowed to embed arbitrary data in the witness and get a discount on it. And even that witness data should be included as a part of a template and verified. So these are two proposals. Reduce the hash digest from 32 bytes to 20 bytes, having maintained the security, and to allow verification of arbitrary data other than op-return, that is data that is in the witness script. Two new suggested proposals by Jeremy Rubin in context with Optech template verified. These are the two news articles that we had. Any questions? Please let me know, or any comments.
One question is that why do you need to include it in on-chain, the Lightning channel update? You can send it off-chain, right? Is there any merit to include it in the transactions?
If you lose the state, or if you lose the state and you send the commitment transaction, okay, I mean it's like the commitment transaction you can broadcast even without maintaining the state. You need to maintain the state, okay. Even if you not maintain the state, every time you update the state, okay, whenever Alice and Bob update the state, okay, they can store metadata that is needed to recover the state, okay. So when they broadcast that transaction on the main net, they can use that arbitrary data to recover the state and spend the transaction in a manner that they wanted to spend, because it's possible that for some reason you just lose the state and you have not saved the state of your Lightning channel anywhere. So you can keep that state stored in the arbitrary data of the commitment transaction, knowing who owed how much.
Right. A tangential related question is that I think this is the use case, if at all there is, I might be wrong, for storing arbitrary data on the Bitcoin blockchain, that it's a natural backup mechanism that all the Bitcoin full nodes in the world will have to keep that data on their nodes, so you can retrieve it relatively easily compared to keeping it on your local system or some other server. Does that make sense?
Yeah, exactly. I mean, I've heard a lot of reputed people that I really look up to, say that there are use cases of embedding arbitrary data, in Bitcoin, and nobody is denying that. Like op return is one of them. Open timestamps. I mean, in Bitshala, a couple of days ago, like somebody questioned about open timestamps. Okay, it's something that I've been exploring off late. Okay, so there are use cases of storing arbitrary data, but not in the manner that they are being stored. Okay, it can be a last resort. It has to be data optimal, and you need to weigh the pros and the cons. Okay, so that is what it is. I mean, nobody
Right.
is ever opposed to the usage of operator. It's being used. Even people who are not in for embedding arbitrary data in the witness script. Okay, they have been using operator. They have been advocating for operator. They have been advocating for open timestamps, which is another mechanism of storing information, arbitrary information in the Bitcoin blockchain. But I mean, they are not okay with storing data that usurps a lot of space. Or I mean, the witness date, the discount that the witness gets was not intended to be used in a way that it is being used today. Is what the primary argument is.
Right. Right. Makes sense.
Okay, just give me 1 second. Yeah, so okay. Okay, we've already covered 1 hour. Let's in 5-10 minutes try and wind up. Okay, because I'm also slightly low today. Whatever it was, I had even that has dwindled now. Release and release candidates. LDK version 0.0.123 is a release of this popular library for building LN-enabled applications. It includes updates to its settings for trimmed HTLCs, improvements to offers, support, and many other improvements. So there is a this is the new version of LDK, which is an implementation of the Lightning Network. Uh, is the release of this popular library. Okay, so a new version has been released. What does it add? Primarily, it updates some setting for trimmed HTLCs. What are trimmed HTLCs? Trimmed HTLCs are HTLCs of like where the transaction is value is so less that it cannot even pay its fee. When you have a UTXO whose value is so little that it cannot even spend its fee, then that HTLC is known as trimmed HTLC. Okay, how these trimmed HTLCs are treated, it depends on the Lightning implementation. Some Lightning implementation, I think, burn these UTLCs, destroy these HTLCs, and some of them, I think, give it to the miner. That entire HTLC is given as a fee to the miner because the fee, I mean, nobody can leverage from it. I mean, the sats that are attached in those UTXOs are so little that it's basically an uneconomic transaction. So the entire UTXO is given to the miner as a fee. And improvements to offers. What's offers? We've also covered offers in preceding sessions. Up till now, what we used to do is we used to send invoices offline, right? If I want to send my Bitcoin address with you, I have to do that over text message or over an email or over a piece of paper. Okay. There's no mechanism for me to send my Bitcoin address to you to receive payments on the P2P network. Once I send you the address outside the P2P network, then you can send a payment through the P2P network. The same happens in Lightning. Okay, if I want to send you an invoice, I have to send you that invoice outside the network, whether in the form of a QR code or whether I copy paste. Okay, all of us who've used let's say for example, whatever wallet of Satoshi, it's a custodial wallet, but just let's take an example because it's a very popular wallet. Okay, what do? We either share the QR code, okay, or we either copy and paste that the string of alphabets and letters and we share it, right? How do we share it? We share it in the form of a text message, or we click a picture of the QR code and share it, etc., etc. Right? It's not shared on the Lightning Network. It's shared outside the Lightning Network. What's offers? Offers basically allows you to share Lightning invoices on the Lightning Network. Okay, so you don't have to send a message or anything. Okay, you just scan a QR code, and from that QR code, an invoice is sent to your node, and then your node will pay the invoice and send it. Okay, so the invoices don't have to be shared outside the Lightning Network. That's what offers is. So this new release add some functionality that are pertaining are trimmed HTLCs and offers optimize the usage of these mechanisms. LD version 0.18.0 beta RC2 is a release candidate for the next major version of this popular LN node. Okay, so LND has also come up with a release candidate, a beta version of a release candidate, which generally has bug fixes before a major version. Let's take this one. Bitcoin Core number 29845 updates several GetInfo RPCs to change the warnings field from a string to an array of strings so that several warnings can be returned instead of just one. Okay. So whenever you would issue this get info RPC, I'm sure everybody who's ever run a node, whether it's on regtest, whether it's on testnet, whether it's on mainnet, has issued this a command. This is generally the first command that you issue using an RPC. Okay, and if there are some warnings, those warnings would come out in the form of a string. Now what happens is that if there are multiple warnings, those multiple warnings come out or are displayed in the form of an array of strings. Initially, you would get one warning. I'm assuming the most important or most SOS warning. But if there are multiple warnings, now you can get multiple warnings in the form of an array of strings, so that several warnings can be returned instead of just one. Okay, let's take one or two more. Which one? Let's take this one. Libsec P256K1 number PR number 1518 adds a sec P256K1 pub key sort function that sorts a set of public keys into a canonical order. This is useful for both music to and silent payments and likely many other protocols involving multiple keys. So we know whenever we use multiple public keys and multiple digital signatures in a Bitcoin script, they have to be arranged in a canonical order, meaning the order in which the public keys are included in the locking script, they have to be signed. The digital signatures corresponding to those public keys also have to be in the same order. Okay, so if it's Alice's public key, Bob's public key, Charlie's public key, then the unlocking script should have Alice's signature, Bob's signature, and Charlie's signature. The order cannot be reversed. Okay. Now, what happens when we're talking about music to and silent payments, right? In these situations, multiple public keys are aggregated, and on the blockchain, you have only one public key. Okay, and multiple digital signatures are aggregated, and on the blockchain, you have only one digital signature. Okay, some enhancements have been made to libsec P256K1 library, which Bitcoin Core uses for all the cryptographical heavy lifting. Is that it sorts the public keys in orders, in canonical order, to ensure that the public keys and the digital signatures, which are off the chain, are arranged in a canonical order and they are sorted properly so that the signature does not fail. That is what this aims to do. What else can we take something? What is this? BIPs 1525 adds BIP 347. So Opcat now has a BIP number. It's 347. I think we talked about this last week as well. An opcode that could be used in TypeScript if it was activated in a soft fork. Adds BIP. Okay, yeah. So what this mentions is that a BIP has been added for Opcat, and if you don't know, I think Opcat is specific to TypeScript. It is specific to TypeScript. So yeah, we have a BIP number that's 347. Opcat has also been deployed on Signet. We talked about it, I think, last week or last week. Okay. It's being tested on Bitcoin Inquisition, and it also has a BIP number that's 347, and it's compatible with TypeScripts. Yeah, that's all I had to share for this week's newsletter. If any closing comments, any closing questions, thoughts, please feel free to go ahead and share them.
Thank you, Faisal, for taking this even when you're sick. Great session.
Bitcoin is my, what do you say, medicine, whatever diagnosis. So I'm feeling better now.
Nice.